Okay, thank you. So last week we have studied the algebraic geometry analog of geometry of numbers. And also we have introduced the notion of adelic curves. So the remaining lectures we will focus on the geometry, arithmetic geometry over adelic curves. So in the morning I will give you some historical presentation on the classical Arakelov geometry over a number field. And in the afternoon I will develop the geometry of numbers for adelic curves. So the basic construction of Arakelov geometry is the notion of arithmetic variety. So you have already seen in the first lecture the geometry of numbers. That could be considered as some geometry of arithmetic variety of dimension 1. So for general dimension, we need some combination of algebraic geometry and geometry of numbers. So we just consider projective varieties, but you should keep in mind that so quasi-projective arithmetic variety also appears in the literature and are very important. So they don't have exactly the same behavior. So, but usually we can consider projective arithmetic variety. So anyway, in my course, so I just consider projective ones. So it just mean projective and a flat morphism of schemes. Which is from X to a spectre of Z. Such that scheme X is integral. So why such thing is interesting? For example, so here you consider some projective scheme. So you can always embed X into some Pn over Z. So just close the subscheme. Then it corresponds to systems of equations. So P1 is 0, xn, 0, etc. Pm 0, xn to 0. So these are polynomials, homogeneous polynomials of certain degree. And you can consider your subscheme as the subscheme of P and Z defined by such equations. So I write this as a system. Then you have a correspondence between X of Z, the integral points of this variety, will correspond to solutions of S, so so integral solutions of this system. So in this way, we can interpret Diophant-time equation systems as integral points of some projective arithmetic variety. And it is expected that the behavior of the solution of the system is determined by the geometric invariance of the scheme. So in a sense that you can, for example, change the variables or change equations. You have different type of equations. So from this point of view, it's difficult to see how to describe the behavior of the solutions. But there are so many conjectures saying that if you know some arithmetic invariance of x, it will determine the behavior. For example, if there is an integral solution or not, if there exists some solution, is the solution set finite, or is the solution set dense for some topology, etc. So all these conjectures are related to geometric invariance of the variety. So it is, in some sense, a very important advancement in mathematics, because in the ancient time there were so many problems about Diophantine equations. So the equation may become very different, but if you know they share some common invariants viewed as a variety, then it is conjectured that you have the same behavior of the solution set. Okay, that is the setting. Now, so what is the relation with algebraic geometry? So that is some idea, very general idea of arithmetic geometry is that, so I write the principle here. So the geometry of x should be similar to algebraic geometry relatively to some curve. For example, relatively to a P1 over some field, finite field or any field. So let me make a table comparing the two sides. Of course, these are very general ideas. So in the realization, you need to do some work. So I write in the left-hand side algebraic geometry. And here, arithmetic geometry. So in the algebraic geometry side, there is some base field. Okay, so very usually it is assumed to be a finite field, but for algebraic geometry, setting is not so important. But just let me assume that base field is finite. In the side of arithmetic geometry, so it is not so well defined. So of course, some people think of the field of just one element. So 0 is equal to 1. But then you have some trouble of developing algebraic geometry on such field, so you need to do some complex thing. So that exists in the literature, however. So let me just put some, so I don't know, here. Okay, so now on the arithmetic geometry side, the basic ring is Z. So here maybe you have already known that the ring of polynomials of one variable over a field have a very similar behavior as Z. For example, they are all Euclidean rings. So they have so many similar properties. So of course here we need to consider some geometry model. So C is PK1. So this is the models for such such ring. So it's so in some sense it's compactification. of spec kt, so which is affine line over k. So here, of course, we can consider spec z. So you observe already that it is not compact, so you need to compactify this scheme. So, but it is not possible to do it in a category of schemes. So you cannot find some proper scheme. So containing spec z. So I use red color to explain the difference. So you need to compactify formulate by some point at the infinity. So there is idea of Arakelov compactification. So now you don't have any skin structure on this set. So any reasonable skin structure on this set. Of course, you have the field of rational functions. So k of c. So here is just the field of rational functions of one variable over k. So on the arithmetic geometry side, it's just the q, which is the fraction field of z. Okay, so now, so the geometry of numbers. So these are basic settings. Then geometry of numbers. So here you have seen that the geometry of numbers are rather geometry of vector bundles. So let me maybe E or C. So here in the geometry of numbers, you consider Euclidean lattices. So maybe I write some E, which is free. It's a module of finite type. So in some sense, these are vector bundles over spectral Z. And then you need to put some norm on ER. So for Euclidean lattices, this norm is assumed to be induced by some inner product. So the geometric invariance here is just the degree of E. So this is an integer. And then you have the Arakelov degree of some data like this. So you have some lattice which can be described in this way. So each with a norm. So here you find the minus log of d lambda. So this is the invariant corresponding to the degree here. So I remind you that this is minus log of S1 with SR for the determinant norm. So here SR is a basis of E over Z. So in general, this is not an integer, but rather a real number. So there is also a big difference with respect to setting here. So now you have a very natural invariant H0 of E, which is the dimension of H0 CE over K. So why I assume that the field K is finite, so I can compute the dimension of this vector space as a log over Q of the cardinal of this global section set. So then here you also have some natural integer. But here, as you have observed, the H0 of E is just the counting of number of elements S in E such that the norm of S is bounded from 1. So this is also a real number in general. So as I have said, so this set is can be considered as the set of sections, rational sections, which has norm less than 1 everywhere. So it's in some sense similar to this set. So here I take log Q that explains the similarity of the geometric side and the arithmetic side. Okay. So now I continue. So in the algebraic geometry setting, we can often consider some, so maybe a P C of R minus 1 maybe. So this one can be considered as, in some sense, like, so we can also often consider projective space. So more generally, we can consider P of E. So this is a projective variety over C. So given a vector bundle, you can consider the projective space associated to the vector bundle. This is the scheme over C. And then on this vector bundle, you have some tautological line bundle, which is OE of 1. So this is the line bundle over P. So now in the arithmetic setting, so of course we can consider PQ R minus 1. So or more generally, so you can consider also PE over spec Z. And also you have some OE1. However, there's something which is not used. So this norm. This norm is not used. So it is not enough here to consider just the line bundle over such a projective space. You need to consider metric on such line bundle. So you should consider some Fubini-Stuti metric. So maybe I use just one bar. So I will go back a little later to the construction of such metric. So let me just introduce some height function. So if you have some P, so write this is pi. It's a section of pi. So the height of P is defined to be the degree of P upper star OE of 1. So you have a line bundle of this variety. You can pull back by such a section to find a line bundle over C. So we have discussed last week how to compute the degree of line bundle. So this degree of line bundle gives the height of the section. So it measures the complexity of the section. So in the arithmetic side, you have almost the same thing. So you take some p, which is a section of this variety. So you may consider this it as some integral points of the variety, and then you can put back OE1 and also the Fibonacci metric, and then you find some Hermitian line bundle on spec Z. So that explains the importance of introducing some metric, otherwise you cannot compute the degree. So you can compute the Arakelov degree of this one. So this is defined as the height of P. So the height function is quite important in the geometry, Diophantine geometry. So that is the side of geometry of numbers. And finally, for general variety, so you just consider flat and the projective map, the projective morphism. Pi from some scheme x to C. So maybe I need to write K morphism. And here, so as you know, these are projective varieties. So projective arithmetic varieties. So it is not enough to just introduce this one, because we need to add some point. Here it is not really projective, so really proper in the sense of arithmetics. So you need to attach some analytic objects. So maybe I write XR analytic. So you need to attach an analytic variety. So maybe I write XC to be sure that you have always points. So XC1. So this is a complex analytic variety which serves to compactify such objects. So I will explain in more details. Just let me give you the comparison table. So here, for computing the invariants of the so geometric invariants, you need to introduce some line bundle. So sometimes the line bundle could be a canonical bundle. Sometimes it could be more general line bundle. So here so here you need to introduce some line bundle. L on X. So maybe I need to use the red color to say that it's different. So here you need to add some metric. So, for example, if you have a line bundle, you can consider the push forward of a line bundle. So that will produce some vector bundle on C, and such construction will correspond to take the global section of L. And then you take some a norm, so the subnorm. So this norm is just defined as follows. You take the norm of S, which is just the superman of X in Xian S by X. And then you can, for example, define an invariant volume of L, so which is the limit sup of n goes to the infinity. So h0 of x, so h0 of x to power n, we divided by n to a power dimension of x over dimension of x factorial. And then on the arithmetic side, so the volume function is defined in a very similar way. So you notice that you need to specify the metric here. So this limit sup of n goes to the infinity h0 hat of such a thing, h0 x to power n, and equipped with this norm over n to power dimension of x over dimension of x factorial. So, for example, it is conjectured that if the volume of the geometric fiber of the canonical bundle so is positive, then the set of integral points in the projective arithmetic variety is not dense. It's not theoretically dense. So this is a very deep problem in arithmetic geometry. So, okay. So now you have such a comparison. So now I will introduce some definitions which appears in the right hand side of the comparison columns. So if you are more familiar with algebraic geometry and find the arithmetic part a little bit difficult to understand, you can use such comparison and to understand such constructions. So let me give you some formal definitions. So we fix X some projective arithmetic variety. So by Hermitian line bundle, X, let me an invertible X module, the line bundle L. So equipped with a continuous metric phi on LC. So this is a pullback of L by the projection morphism XC to X. So you can change the underlying ring. So you change X over Z to XC over C, and you pull back the line bundle on XC. Then you can equip with a metric. So I will explain a little bit. So what is the metric? So as you know, XC is just the X times fiber product over spec Z, spec C. So then you can attach some analytic variety. So we change the topology of the scheme. So this is just a space of complex points of the scheme plus analytic topology. So if you are not familiar with analytic topology, you just can consider it as some differential variety. So you have some topology, Euclidean topology, locally Euclidean topology. So I don't talk about the analytic functions. So just as a topological space, it's just the subset of some Euclidean space. Locally a subset of Euclidean space defined by your system of equations. So now, you have some LC. So phi on LC is just a family of norms. So so the norm at x is a norm of x up star your LC. So here x is a complex point of x. So you can put back your line bundle by your x, your morphism x, and then we require that for any u in XC, which is a Zaleski open set, and for any S in gamma of mu LC, then you can find a function, so you can evaluate the function locally at any point x in C. So this functions for UC to R is continuous. So we just require that the function defined by the evaluation of norm, so is always continuous if you take so algebraic sections of the line bundle. So just orally, I mentioned that you need also require that the metric should be invariant by the complex conjugation. So because you are working with Z, so you make a change of ground ring, and on spec C you have an action of complex conjugation. So that action will induce some action on the metric. So you need to assume that the metric is invariant by complex conjugation. So it's not so important. So I will not give the detail here. So now, if of course, if you have a global section, so you can define S phi as the superman of x in xc, S phi of x. So this is always positive, non-negative real number, because you have a continuous function on some compact set, and you always have its maximal value, which is not infinity. So now is there such thing? So maybe sorry. So maybe I should write XA. No, say. So now this one is a norm on such set, gamma of XC, LC, so which is also invariant by complex conjugation. Okay. So now it is expected that on the right hand side you have similar results, constructions results to the left hand side. But this is just some very, so anyway, so if often very formal comparison does not mean that you can copy proofs on the left hand side to the right hand side to prove anything in arithmetic geometry. So for example, there are very deep conjecture like ABC conjecture, which could be proved in left hand side, but remains very deep problem on the right hand side. So for example, if you look at the literature on ABC conjecture in the arithmetic setting, you notice immediately that the method is very different from the geometric method. So of course we can give many explanations to the difference, but I will give you some easy one. So you observe, you can observe this set of global sections is inside the unit ball. So I just make some graph. So imagine that you have some Euclidean lattice, and then you can draw a unit disk. So this is similar to H0C here. But this set is a vector space over a ground field. At least it is a group. It is stable under addition. Now if you take 2 points here and here, you try to calculate their sum, you find a point which is outside of the unit disk. So you don't have any reasonable algebraic structure on such set. So that is one of the main difficulty, at least for the study of the arithmetic volume function. You don't have so classical techniques of Davisage. You cannot write a heap polynomial, so it is not a polynomial. So anyway, so the volume here is, so anyway, the H0 here is not an integer, so there are something which are very different. So our purpose is to propose some method which works simultaneously here and there. So that is the motivation of our joint book. So let me explain a little bit how to do it, but in a very classical setting. So then you will get enough motivation to study a very general framework. So before that, I will talk a little bit about geometry of a trivially valued field. So apparently that is quite different from these two parts, but our main method is to make a projection of the very different geometry to the same geometry of trivially valued field. And then you get reasonable arithmetic invariants or geometric invariants from the geometry of trivially valued field. So so let me fix some field, and the plus. So this is a trivial valuation. So absolute value. So you have already observed last week that this setting is a particular case of adelic curve. So then you have some trivial product formula, etc. Then, so fix also some vector space of K of finite rank, and also an autometric V. So this is the some adelic vector bundle on the adelic curve defined by such data. So just a little remark. So first one, for any positive radius, so if you consider the ball of radius r, this is a vector subspace. Of V. So the reason is that you have an arithmetic norm, and therefore you have some strong triangle inequality, so that this set is invariant by addition. And then your field is trivially valued. So if you multiply by some non-zero vector, non-zero element in K, non-zero scalar, you will not change the norm. So you stay in the ball. So you have just some vector subspace. And the second observation is that if you consider all balls so this is just a finite set. So maybe I exclude the zero ball. No, it's not necessary. So I just consider all balls. And this is a finite set, and the cardinal is not more than dimension of V plus 1. Okay, so what is the reason? So then you observe that this is somehow a totally ordered subset of the set of all vector subspaces. So if you have two balls that are different, their dimension should be different because they can be compared. So you have just the dimension K of V plus 1 choices for the dimension of subspaces. So you have not so many choices. And therefore, so you can write this set as a sequence of vector subspaces. So there you will observe something which is very similar to Hadana-Simon filtration. So it can be written in a form of 0 equal to V0 contained in V1, Vn, which is V. So here n is at least dimension K of V. So at most such dimension. So so for each I, we just write a new I, which is minus log of a supremum of x in Vi. So you could have different radius. So different radius may produce the same ball. Just pick the largest radius possible. You take a minus log of this one. And of course, by definition, you will have mu1 bigger than mu2, etc. bigger than mun. So now I can draw a map. So you can fit the data into a map like this. So you have mu1, mu2, mu3, etc. Mun minus 2, mun minus 1, and mun. So you have some decreasing sequence. So you begin with V, which is Vn. And then you put Vn minus 1 here. So here the coordinate is rank of Vn. Sorry, I should know this one. So here the point here, the coordinate here is rank of Vn. So here you find the rank of Vn minus 1. And here you have Vn minus 2, rank of Vn minus 2, and etc. And then you have some V3 here, V2 here, V1 here, and finally V0, which is 0. So here you find rank of V1, rank of V2, etc. So you can draw a picture. You put everything in this way. What do you get then? You get some R-filtration. You get a family FTV. Some R-filtration of the vector space V. So it's just the family index of vector subspaces indexed by R. So which becomes 0 when T becomes larger than mu1, which becomes V when T is less than mun. And this function, so if you consider the rank of FTV as a function on T, so this function is left continuous. So if you begin with such a filtration, you can also recover a flag, a sequence of vector subspaces, and some ui, which will give you an ultrametric norm. So you have three types of things which are different, but they have one-to-one correspondence. They have one-to-one correspondence between ultrametric norms and the flag, flag of vector subspaces with a decreasing sequence of slopes, and also this R-filtration. So you can change freely between amongst these three types of objects. Okay, so it's better that I write on the table because these are important. So there are canonical bijection. First of all, a set of pairs. And also mu1 measure the mu n. So second set of all filtrations of V, which is defined in such a way, so get some family of subspaces parametrized by R, and finally a set of ultrametric norms. Okay, now I can define the Arakelov degree. So it's just a minus log of S1 etc. Sn. So here Si is the basis of V over K. So now you can wonder how you calculate the same invariant by using the language of pairs and R-filtrations. So I will just give you a formula. So this is just the sum of I. Sorry, so I should not write N here because I need N to denote the length of a flag. So So one way to compute this invariant is mu I times the dimension over K of the quotient space Vi over Vi minus 1. And then now you observe that it is somehow, so if you took you take this graph, so dimension of Vi over Vi minus 1 is just the size of jumps. So if you are familiar with distribution, so you'll find that this is just a minus integral over R t time d of the function dimension over K ftv. So in some sense it's a fancy way to compute such Arakelov degree. Integral of t with respect to such distribution. So you just have a stairwise function, and the distribution of such a function is just the sum of the Dirac measures on each coordinate of jumps times the size of the jump, and which is just here. Okay. Now, what is the relation with today's situation here? So maybe I need to erase somewhere. Okay, so So you have already seen that for Hadana-Sima filtration, you got something like this. You got a flag, and you got a decreasing sequence of slopes. So that comes into the geometry of vector bundles. And I will explain how to obtain something similar. So now that E be an adelic vector bundle over Q. So maybe it's better to take this point of view. So you have E some free Z module of finite type. and you have some norm. Okay, then I will give you the definition of an R-filtration. So you take Ft of E bar, which is a vector space over Q generated by sections in E. So with the norm of S smaller than exponential minus t. So now when t becomes large, you have a smaller, you have a smaller radius. For example, if you take t very large, and then you have just a very small small ball. You just find the origin inside the small ball. So the vector space generated is a zero vector space. And if this becomes a little bit larger, so you have something here, and which generates a vector subspace of rank 1. And if the radius becomes really large, you find a basis. So this one is an R-filtration of EQ of this vector space. And you have some relation with successive minima. So you have already seen that. So let me just give you the first definition: mu I of E bar, which is the supremum of T in R, such that the dimension of Ft E bar is greater than I. So in this graph, you just find some I here, and then you take the first coordinates that your function attains I. Now what you can observe is that the new one of each is just a minus log of the lambda mean of lambda. So if corresponding to some lattice, lambda. So in the first lecture, I have given the definition of lambda mean, so which is the radius. So the length of the shortest vector inside the lattice, which is non-zero. And then if you take this point of view, you find that it's just a minus log of this radius. And of course, you have another invariant, which is smallest radius that your ball contains a basis. So that is the smallest ball that vector space generated by such thing is the total vector space. Therefore, you have nu of dimension, so maybe of rank, so inside R to n. So you have a new n of each, which is just the minus log of lambda max of lambda. So you see such invariants can be described also by R-filtrations. So in some sense, R-filtration will build up a bridge between these two sides. So in the geometry of vector bundles, you have Harden-Narasimhan filtration corresponding to R-filtrations. But here you have successive minima corresponding also to R-filtrations. So why such thing is interesting? So now let me go back to the higher dimensional arithmetic varieties. So now let X be a projective arithmetic variety. And L be a Hermitian line bundle. And I take En, which is H0. So here I write L as L equal to with some metric. So En, maybe En bar, which is H0 of x L to power n. And then you have some norm, which is a subnorm corresponding to N5. And then what will you do? So you take just Vt of L. So I define this as, so I take maybe Vt and L, which is F. So F is such a filtration and T. And then I take this En. So I consider the Q vector subspace generated by a lattice point of radius exponential minus NT inside this lattice. Okay, so claim is that if you take Vt points of L, so which is a direct sum for n inside n, so F and T of En. So this is a graded Q algebra. So it's a graded sub-Q algebra of such thing. So the sum of H0 XQ LQ. So if you are familiar with algebra geometry, you find this Cox ring of the line bundle LQ, and this is just called a graded linear series. So you find a graded linear graded sub-K algebra of somehow nice graded algebra. So the advantage of introducing such a geometry of trivially valued field is that you obtain something which have a very nice algebraic property. You have something which is stable under addition and multiplication. So it's
maybe you forget the tensor product.
Yeah, I forget the tensor product. Sorry. Thank you. So tensor power n. Yeah, you're right. Yes. So because here En is some vectors, so some subset of. So sorry, En is this thing is subset of this vector space. So you take vector subspace generated by something. Okay. So that is very interesting because you have the link with algebraic geometry. So I will just let you to check that this is stable under multiplication. So maybe it's not too hard. So this is not enough because our purpose is to recover this H0. So you have something which is geometrically nice, but you need some arithmetic data. So let me introduce a theorem of Gillet and Soulet. I will not explain the proof here. So, but to understand this theorem, you can refer to somehow geometric version of the second Minkowski's theorem. somehow like that. So the theorem says that there exists an absolute constant C such that for any lattice or adelic vector bundles over Q, E bar, which is the E vector norm. So you have you can compare H0 hat of E, which is log of coordinates, so log of cardinal of elements in the unit ball. So minus sum for any I from 1 to the rank of E. So max of nu I of E and 0. So this one is controlled by C times of times rank E times log of rank E. So this is not that far away from such H0 hat of E. Then just I come back to such equality. So instead of computing the degree hat, so such like this integral of t such a thing. So so here, if you compute the integral of t, you find the degree, which is in some sense the sum of all nu I of E. So here you just have the integral on positive. So t d of dimension k. So here is dimension q, ft of E. So then you can make a change of so how to say integral by parts. So you find this is just the integral of 0 to the infinity dimension q ft of E dt. Now you observe really a strong link, because then you have such a construction of a family of graded linear series, and the dimension of each component is closely related to H0 hat, because it appears here. Dimension is if you integrate the dimension, you recover almost the H hat 0, of course with some error term. So I will explain what we can do with such techniques. So, but I will rather explain this a little bit later in the general adelic curve setting. So let me just recall some of the basic invariants here and the results, statements of results. So always you have some comparison on the two sides. So for example, if you have an integral projective scheme, so maybe over some few cases, and V is dimension of X. So here I don't consider any relative structure of the scheme over some curve. So, but you still have some similarity. So you have some the X on specular seed. And then D is the dimension of X. Now, if XL is invertible, or X modulo, so here you have L bar, information line bundle. So you have a volume of L, you have a volume hat of the L. So you have observed the definition there. And there are some properties. So if you take a volume of L to some power n, so you find n to power d times the volume of L. So here you have the same thing. So you have a volume hat of L power n. You just have the n to power d, volume hat of L. So, so if L is ample, then such volume L can be computed as the degree of the intersection product. Here we also have the same thing. So if so L is ample, and so maybe I write L here as L5, and the phi is semi-positive. And the height function. So height function defined as h p is the degree height of p up star alpha. So if the height function is positive, then you will have the volume of L bar is given by the degree height of the arithmetic intersection product. So this is known as Hippo-Samuel type theorem. So it's proved by Siegel and Bush. So each time you find something which is rather standard here, and you find something which is complicated or more evolved here. So I mainly give some reference to on the arithmetic side. So so for example, L isn't big. So volume of L is positive, namely L is big. So if and only if you can find some A ample, such that H0 of X L2 power, so you can find some n. So L2 power n tensor A0 is not 0. So you can find inside some power of your line bundle something which is larger than an ample line bundle. And here you have the same thing. So the volume heads of L is positive, if and only if you can find some A A bar, which is ample. So I will not give you a definition for ample, but it's almost the same thing to say that to say the condition here. L is ample, line metric is semi-positive, and the height is positive. So you can find some n such that h0 hat of L to power n times a0 is not 0. So namely in such lattice you find some non-zero lattice point in the unit pole. Also so this is not so difficult to prove, but this one is difficult. So you have a continuity So, for example, you have L and M, two line bundles, such that the volume of L is positive. Then you have a limit of n goes to the infinity 1 over n of 2 power d, volume of L to power n, and the tensor n is the same thing as the volume of L. And then you have the same thing, so you have a Lm, it's the volume of L positive, so this is the theorem of Moriwaki. Okay. So you have exactly the same thing. So limits of n goes to the infinity 1 over n to power d volume heads of L to power n tensor m. So this is the volume of L. So also in the definition you have some limit sup. It's actually a limit. So here you have the same thing. So this is firstly proved by myself by using such techniques. And you have some Fujita type theorem. So in some sense it's a little bit like this. So if the volume of L is positive, then for any epsilon positive you can find some A ample and the n which is a positive integer, such that h0 of x L to power n tensor n dual a dual is not 0, and also the volume of a over n to power d is almost the volume of L. So it's volume of L minus epsilon. It's almost at least volume of L minus epsilon. So not only such thing contains some ample line bundle, also such ample line bundle gives a volume which is very similar to that of L to power n. So maybe I will not write the detail, but you have a very similar result. So this is proved by independently by Yuan and myself. So this is formally a conjecture. These two things is formally a conjecture of Moriwaki. So each time you find something which is more or less classical on the left-hand side, and they are relatively new and more complicated on the right-hand side. So you also have differentiability. So this is not that classical, is more recent work of Buxon. Johnson. So so assume that L is big. Then the limit when n goes to infinity, the volume of L to power n times m minus volume of L to power n. So maybe so this is such thing divided by n to power d minus 1. So such thing exists. Not only such thing exists, but also and is a linear form on M. So here you have a similar result. So it's proved by myself, but using somehow a very similar idea. Okay, so that will give you an image of what we can do. It's the left-hand side and the right-hand side. Okay, so the purpose of the coming lectures will explain how to apply such techniques of R-filtrations to general geometry of higher dimensional variety over an adelic curve. So as I repeat that the method consisting of projection procedure of geometry over higher dimensional varieties to some geometry of R-filtrations of adelic curve of just one field with trivial valuation. So maybe in the afternoon I need to do some work on the geometry of numbers in the setting of more general adelic curves. So I just stop here and I will continue in the afternoon.
Okay, so do you have a question or comment? Okay, let's thanks again. No.